Are there hidden benefits to climate change that people don't talk about? More specifically, what's the actual science behind the common suggestion by some that CO2 is plant food and therefore more of it is good, not bad? Well, let's discuss. My name is Mallen Baker. This is the Mallen Baker Show for Changemakers. A couple of weeks ago, I did a video about the role of CO2 in climate change and specifically what was the science behind the claim that CO2 was saturated. In so doing, I made a passing jocular reference to shooting a cute dog at point blank range. Well, alright, no, actually I didn't. I made a passing reference to one of the comments I sometimes get in all caps in the comment section of my videos, CO2 is plant food. And I dismissed it as a red herring. And I think I would have got less kickback if I'd shot the cute dog. I had lots of people telling me, no, you've got this all wrong. This is a serious argument and you're dismissing it way too lightly. The learning point there is if somebody represents your argument in all caps in a YouTube comment section, it's not going to represent your case in a way that's going to encourage people to take it seriously. But I listen to kickbacks. And obviously this is an argument that's out there a lot and some people put quite a bit of weight behind it. So let's step back, shove out all of the assumptions and preconceptions and let's have a look at the detail. At the heart of this discussion is a basic realization that shouldn't be a surprise to anyone, but which some people resist fiercely, which is that when a complex system like the Earth's climate undergoes a change, there will be a range of impacts. You can expect some to be beneficial. Of course, then some to be damaging. And the question then becomes whether you can embrace a nuanced discussion to look at the evidence as to the positives and to the negatives. So one of the most notable people that makes this argument is the American physicist William Happer. Here's a quick clip of him doing just that.
It's a perfectly natural thing, and in fact we're in a bit of a carbon dioxide famine now. If you look over geological history, it's been much higher than now most of the time. Most plants do better with more carbon dioxide than they have now. So it's just a complete distortion of the truth to call it a pollutant. It's not a pollutant at all.
When did this start becoming a pollutant and not just the naturally occurring material that we all heard about growing up?
Well, I think it began to get legs in the 70s and 80s. There was a Academy of Sciences report by Charney in the 70s, and then it got latched on by green politicians. Al Gore is a person who comes to mind, but there are many others. And so people saw a way to make a buck in demonizing CO2, and that's what's happened.
To be fair, in that clip, there's not a huge amount of nuance in Happer's position. According to him, it's all upside. But it's just a clip, not an exhaustive review of what he's said and written. So we won't jump to any conclusions from that. We'll just take the arguments as they are. The first thing to note is that he's right about the starting premise. We can show demonstrably, under controlled conditions, that many plants, when fed more carbon dioxide, grow faster. And this is why commercial greenhouses pump in additional CO2 for their crops, going up to something like 1,000 parts per million, up from the 400 parts per million, which is the current concentration of the atmosphere. They do this because they get more growth and higher yield from their plants. Happer says that higher CO2 also helps plants to conserve water. We'll talk about how that works in a moment. He also points out that we had much higher levels of CO2 in the age of the dinosaurs when there were similarly high temperatures and the vegetation was doing very well at the time, thank you very much. And his final point is that while people are now eulogizing about 280 parts per million, which is the pre-industrial norm, as being some sort of golden age of ideal carbon, the level has actually been all over the place in the past. 1,000 to 2,000 parts per million has been known through many millions of years of prehistory, and according to Happer, it was fine. Instead, he complains that CO2 is now being regarded as a pollutant, but in reality, it's a valuable gas that is essential to life, and indeed, to support that argument, NASA has reported that due to the increased CO2 levels in the air to date, we are already seeing a certain amount of greening on the Earth, which is attributed to CO2 fertilization. according to a study published in Nature Climate Change on April 25th last year. From a quarter to a half of Earth's vegetated lands are showing significant greening. That greening represents an increase in leaves on plants and trees equivalent in area to 2 times the continental United States. The study came from an international team of 32 authors from 24 institutions in 8 countries, used satellite data from NASA's Moderate Resolution Imaging Spectrometer and NOAA's Advanced Very High Resolution Radiometer. Carbon dioxide fertilization isn't the only cause of the greening. Nitrogen, land cover change and climate change impacts in temperature, rainfall and sunlight, all of those have an impact as well. But the CO2 increase takes the lion's share of that impact at approximately 70%. To support those real-world observations, you can demonstrate the effect in the laboratory. For instance, HAPA quotes tests at the University of Arizona, which showed the impact of growing certain plants with 385, 535, 655 and 835 parts per million. In that study, the plants grew progressively better in all the cases. There's no reference to the study that is pictured, but other studies have shown similar things. Of course, really, you need to carry out studies that mimic the outdoor growing conditions, studies that use what's called free air carbon dioxide enrichment, or FACE for those who like their acronyms, where crops are grown outside and exposed to higher levels of CO2. A review of those studies, linked in the video description, showed that plants given an elevated level of CO2 responded with increased photosynthesis and growth. To some extent, this benefit was dependent on other factors. In commercial greenhouses, the plants that get enhanced CO2 also get an optimum amount of other things, nitrogen, fertilizers and water, for instance. In the trials, lower levels of nitrogen reduced the amount of additional photosynthesis and growth. So the degree of impact in real-world situations would differ and would certainly be less than can be achieved in a greenhouse where plants are given the absolutely best conditions. Still, if NASA is showing noticeable greening in the world right now, then clearly there is a measurable impact. In addition, food crops grown with elevated CO2 showed reduced amounts of protein and other nutrients, specifically minerals. So while the quantity of the crop increases, the quality decreases. If they're used for animal feed, animals would need to eat more to achieve the same nutritional benefit. Samuel Myers, principal research scientist at environmental health at Harvard University, estimated that at a concentration of around 550 parts per million, food crops could lose enough of their key nutrients to cause protein deficiency for 150 million people and a zinc deficit for another 150 to 200 million. Obviously, that may be a problem we can see coming and in theory address. I mean, when we get those sorts of stats, they kind of assume the world sits still and just waits for the negative impacts to kick in. But then again, you should bear in mind, we already have significant numbers of people living with that sort of nutritional shortfall. So it's by no means a given that we will organise ourselves well enough to deal with it if it becomes a problem. Richard Norby, a corporate research fellow in Environmental Sciences Division and Climate Change Science Institute at Oak Ridge National Laboratory, also underlined this point. Norby said that in a complex world, there are many other factors involved in plant growth, in untended forests, fields, and other ecosystems. He said this: if nitrogen is limited, the benefit of a CO2 increase is limited. You can't just look at CO2 because the overall context really matters. According to Dr. Philippe Ciais, Associate Director of the Laboratory of Climate and Environmental Sciences in Gif-sur-Yvette in France, the impact may have diminishing returns. And he said this: studies have shown that plants acclimatise or adjust to rising carbon dioxide concentrations, and the fertilisation effect diminishes over time. And Richard Norby agrees. In trials he's been involved with, he says that artificially doubling CO2 from pre-industrial levels was shown to increase the productivity of trees by around 23%. But again, that effect significantly diminished over time due to nitrogen limitation. He said this: we cannot assume the CO2 fertilisation effect will persist indefinitely. Now, as HAPA says, one of the other impacts of enhanced CO2 is that plants may lose less water. With an atmosphere more rich in CO2, the plants don't need as many stomata open for as long in order to absorb the amount of CO2 that they need. And that matters because while the stomatas are letting CO2 in, they're also letting water vapour out. So reducing the amount of time they're open or enabling the plant to do without so many in the first place means potentially beneficial water conservation. That obviously can have a beneficial effect of helping plants to be more robust in the face of reduced rainfall or even drought. It can have the less positive knock-on effects in some environments of increased soil moisture levels leading to increased runoff. So again, it depends on the details, it depends on the context. Now, not all plants respond in the same way. In particular, there are two main types of plants that are quite different, which are known as C3 and C4 plants. The differences come in how they go about the process of photosynthesis. For C3 plants, which are in the majority and include crops like wheat, rice and soy, the impact of increased CO2 is significant. For C4 plants, which can also include some important crops such as maize and sorghum, the impact is minimal. Why is that? A very quick canter through the science. In C3 plants, air comes into the leaf via the little holes we've already mentioned called the stomata, and there the CO2 is captured by an enzyme called rubisco, so it can be used in photosynthesis. This then goes into a biochemical process called the Calvin cycle, and without going into the mechanics of it, it uses the CO2 to create two molecules of free phosphoglycerate, which is then used to create glucose. But that enzyme can also bind oxygen. It prefers CO2, for which it has 3 to 4 times more affinity than it does oxygen, but it can end up with oxygen nonetheless. If that happens, then it triggers a different process called photorespiration, which is much more wasteful. So the calculation's a simple one. If there is more CO2 in the atmosphere, it is even more likely that the rubisco enzyme grabs the CO2 and not oxygen, and that increases the efficiency of the photosynthesis. So why does that result in reduced quantities of protein and other minerals? Short answer, we don't know. As always, we're finding new things out all the time. If we discovered the mechanics of that process, it could be that there'd be things we could do to minimise the negatives whilst enhancing the positives, but it's a long way off at the moment. Certainly not to be counted on. Anyway, that's C3 plants. Why are C4 plants different? Well, C4 plants have a different process for photosynthesis. They use a different enzyme to capture CO2, PEP carboxylase, which has a much higher affinity to CO2 than oxygen. And before passing it into a Calvin cycle process, it converts the CO2 to another chemical malate, so you only ever get one optimum process fed by CO2. There's no secondary process that can be triggered by oxygen. Now, the real-world expression of these differences is that C3 and C4 plants thrive in slightly different conditions. The optimum temperature range for C3 crops is between 15 to 20 degrees centigrade. For C4 crops, it's 25 to 30 degrees centigrade. The functional makeup of C4s makes them better adapted to live in hotter and drier conditions. And that introduces another key factor, because the amount of CO2 doesn't exist in a vacuum. There's also the question of temperature. If the equation was just about what happens with increased CO2, then it's largely good news, even with the unwelcome impact on nutritional quality. But then there's the fact that we expect rising temperatures to match that increase in CO2. You can see some of the mechanics of that in my previous video on CO2 and the molecular basis for why it leads to warming. So how much difference do we think it's going to make to the yields of different staple crops, based on the benefits they'll get from the increased CO2 and the temperature? According to Carbon Brief, which summarises research fed into the IPCC reports, with a 1.5 degree average global temperature, we would see wheat globally up by 2%, soy globally up by a significant 7%, rice globally also up 7%, maize globally, remember maize is a C4 plant, so not such a beneficiary of the additional CO2 concentration, down by 1%. Now those are global averages. The additional heat becomes more of a factor in the tropics, where these crops already live close to the ceiling of where they're comfortable. In the tropics, wheat would be down 9%. Soy and rice would still be up at 6%, just 1% down on the rest of the world. and maize would be down by 3%. But let's be honest, restricting warming to 1.5 degrees seems unlikely now, so what do the changes look like when we get to 2 degrees centigrade? At that level, we would expect wheat globally to be back to zero, so its yield would be the same level as it is today, with the exception that its nutritional content will be down, so it's actually a net loss in nutrition. Soy globally would still be up, but just by 1%. Rice globally would be unchanged, being up by 7%. Maize globally would be down by 6%. In the tropics, we get quite a mixed picture. On the negatives, wheat would be down by 16% and maize down by 6%. So that's a big deterioration for wheat. The picture for soy and rice is more positive, being up by 7 and 6% respectively. If it just stays at that, that's a tolerable transformation. It isn't that simple, because one of the things that will come with those scenarios is more frequent instances of weather extremes. So more droughts in some areas, more deluges in some areas, sometimes going from one to the other in the same area, from one year to the next. The elevated CO2 does give some help in the gentler end of that spectrum. Studies have shown that elevated CO2 can help the recovery of plants from periods of high temperature induced stress. Soybeans were subjected to an 8-day period of high temperature and water stress, and after normal conditions were restored, the CO2 enriched plants regained rates of photosynthesis at 72% of the norm, while the control group only attained 52%. But the CO2 enrichment in that study was significantly higher than the real world conditions we expect or want to be experiencing at 700 parts per million. Therefore, those particular benefits of enhanced CO2 would be significantly reduced in the real world. So that's a relatively quick canter through what we know about the impacts on plants of enhanced CO2. One comment, by the way, on William Happer's argument that CO2 isn't a pollutant and that this was something that was invented by green politicians. When I used to work with businesses on environmental management in the old industrial north of England, I used to point out to them the real definition of pollution that they should take as a working definition, which is that pollution is a valuable chemical that happens to be in the wrong place. And in some ways, it's the same as the definition of a weed, which is a perfectly good plant in the wrong place. In other words, whether something is a pollutant or not isn't about whether a substance is useful in one context, but whether it's harmful in the environmental context where it ends up. For example, nitrogen, which is useful in the ground as a fertilizer, becomes a pollutant when it runs off into rivers and ocean, where it can lead to algal blooming. In the same way, CO2 is a useful gas used by plants for photosynthesis. Those benefits are less significant than the expected negative impacts from a warming world. And this is why the focus goes to the impact of global warming. If you don't believe that CO2 leads to global warming, then the mix of benefits and disbenefits from enriched CO2 in the atmosphere is, on the face of it, unless we learn of other consequences not yet in the frame, not that bad a thing in itself. But in order to get there, you have to be in a world where the additional CO2 doesn't cause warming. And that's not the world that the evidence currently suggests is our home. And no, it's not about CO2 directly being harmful to human health. As Happer's fond of pointing out, in a room full of people, you may get to a couple of thousand parts per million of CO2 just because of all the people breathing. The limit considered safe if you're in a space capsule is 7,000 parts per million. So no, that's not the issue. The real challenge with all of this is how binary it all gets. We should be able to have a discussion where we discuss the relative interplay between positive and negative impacts of the growth of CO2 without people on either side jumping in to claim it's only a benefit or it only spells doom and catastrophe. There are plenty of reasons why we need to take action to stop the growth of CO2 emissions, and the benefits don't offset the negatives to the degree where we should start to think it's not needed. So anyway, there it is. At the beginning of this video, I compared the reaction of my passing reference to the benefits of CO2 on plants as being akin to me shooting the cute dog. Since I have now been duly humbled for dismissing serious arguments too lightly, I will now proceed to make amends by shooting the cute dog. This is your fault.
Dig 'em up!
See? Aren't you glad you stuck with this video right to the end?